these nonlinear properties of some particular magnetic colloids, which is named ferrofluids. And we will see by the end of this talk what's the take-home message, which is about some measurement of the nonlinear optical susceptibility, electric susceptibility of this material, where we can have some idea about how an isotropic is a cubic structure present in some particular magnetic colloids. This work was done in the University of São Paulo, Brazil, 3 hours from here by plane. And this is the outline. Basically, we will speak about, to define these magnetic colloids, how they respond to the magnetic field, something about nonlinear optics, which is basically the essential of this talk. I will tell you some hints about this Z-scan, which is the experimental technique that we use to access these nonlinear optical properties. Basically, we will measure the nonlinear absorption and nonlinear index of refraction of these colloidal materials, and some conclusions in the take-home message. Well, ferrofluids essentially are magnetic nanoparticles, typical diameter of about 10 nanometers here, and they may be ionic or surfacted, and you can put these magnetic particles in different types of solvents, polar solvents like water, or non-polar solvents like different oils. And to keep these particles in a stable solution, you have to compete with the van der Waals attraction, with something that make the particles apart, with respect to the other. And to do that, we can charge the particles with electric charge. So we have the competition of the van der Waals attraction and the repulsive electrostatic interaction. Or you can put around these particles some amphiphilic molecules, and these amphiphilic molecules will provide some type of steric interaction, which will keep these particles in a stable solution. Well, this, as I told you in words, is essentially the distance between two particles. Here you have the repulsive attraction, the van der Waals attraction here, the repulsive interaction here, and the van der Waals attraction, and you have a typical dimension or a typical distance between particles, which is about some tenths of nanometers also. Well, when you prepare a ferrofluid, there are many different ways to prepare this type of particles. And when you prepare this, for example, by chemical synthesis, you can have here is the probability to find particles of a particular diameter and the diameter here. And you have this type of distribution function, which is well described by a log normal distribution function. So basically, you have this type of distribution functions in an actual ferrofluid. And this actual ferrofluid, this is some examples here. We can have, for example, spheres, almost spheres, the particles with this type of geometry. You can have cubes that are very interesting type of ferrofluid that we can synthesize just for changing some atoms and the method of the chemical synthesis. And you can have also a mixture of spheres and cubes. And the typical diameter here is about 20 nanometers. This is the scale just to give you an idea. This particular ferrofluid were synthesized in India by a group. They're very good chemists. Well, in the presence of a magnetic field, you have a very nice type of structures from the nanoscopic point of view up to macroscopic like this. So this is a ferrofluid where you put a magnetic field perpendicular to the film. So you have this spikes here, which is named essentially Rosenzweig instabilities. So depending on the strength of the magnetic field and some properties of the colloid, you can have this type of structures. Well, so typically in a ferrofluid particle like that, you have about 10 to the 3 to 10 to the 5 Bohr magnetons for the magnetic moment of the grain. And when you put in the presence of the magnetic field, what you can have basically two types of process, a physical process. One of them is named neo rotation, where you freeze the magnetic moment in a direction not exactly parallel to the magnetic field, but mainly in the direction of the field. Or you can have a physical rotation of the grain, which is named the Brownian rotation. So these two types of behaviors, they have a characteristic relaxation times or typical response time, and depending on the strength of the magnetic moment and the viscosity of the medium you have this here around, you can have both types at the same process. Well, if you imagine, for example, these magnetic particles randomly distributed in the colloid, in the magnetic colloid, if you are with a magnetic field smaller than the first critical magnetic field, what you have is basically the orientation of the moments, but without the formation of macrostructure. If you increase more the field between this first critical field and the second critical field, you have the formation of some lines. Okay, they align, and more than this, they attach one to the other and make this type of linear aggregation. We will basically study this type of structure in the following. But if you increase more the field, and the field higher than this critical field, the second critical field, you have the formation of bundles. Essentially, you have these stripes that you come together and make something bigger with the magnetic moment mainly oriented along the direction of the magnetic field. So this we try to avoid in the case of the study of the particles. This we try to avoid also, but it's not so easy because this H1 and H2 are not so different. So if you are in these two conditions, it's interesting for study the magnetic and electric properties of the magnetic grains isolated. Well, these ferrofluids are essentially named super paramagnetic. They are not paramagnetic because we are not treating with the spin of atoms, of electrons, but we are dealing with the magnetic moment of a grain, which is much higher than the spin of one electron. So it's named super paramagnetic because of that. And one particle of a grain like this, they have essentially one magnetic domain per particle. So it's so small that you have just one magnetic domain. You don't have more than this in one particle itself. And obviously, you can have, if the temperature is large enough, we can have this flip of the magnetic moment inside the particle. These are essentially the anisotropy of magnetocrystalline constant, the volume of the particle. So this is the time of Diniel rotation. This time here is essentially of this order of magnitude. And the temperature is different. If you load the temperature, you can achieve in a system which are named blocked. So we will block the magnetic moment in the particle, so the magnetic moment will not split as a function of the time. And if you change the temperature, you can go to a super paramagnetic to a blocked state. So this is a very interesting system that, because these temperatures are very easy to be achieved in laboratory. You don't need to go to very small, very low temperatures to do this type of investigation. Well, let's speak about the nonlinear optics. Is that what we will discuss mainly in this topic? So when we study electromagnetism in high school or in college, we know that the polarization is proportional to the electric field, but this is not the whole story. Depending on the strength of the magnetic field, you can have high orders in this total polarization that will be induced by the electric field. So this is the linear term for the polarization. This chi1 is essentially the linear susceptibility, and you have the second order susceptibility, third order susceptibility. You may identify here the intensity of your beam, of your laser beam, for example. So these are essentially the high order susceptibility, and depending on the type of experiment you are interested to do, you can investigate the different types of susceptibilities. Mainly, if you are interested in an isotropic medium, like magnetic colloids that we have here, by symmetry reasons, this term will be 0, And the first time, in the first term, which is non-null, non-zero in this expansion here, is the third order susceptibility. And this third order susceptibility will give us the possibility to calculate the nonlinear index of refraction and the nonlinear absorption. Well, so as I told you, these susceptibilities here are mainly determined by the symmetry properties of the medium. And if chi2 is 0 in a centrosymmetric medium like magnetic colloids, they are isotropic without the application of the magnetic field, you have an effective susceptibility here, which has essentially two components. One of them is the linear one, which is always present, and the second one is the next non-zero of this expansion, and the chi3, the third order susceptibility, and here is the intensity of the beam. So we can write the index of refraction of the material as a linear part here, which is the usual index of refraction we know, we can measure easily in the lab. But you remark that here you have a correction to this term, where the N2 is the nonlinear index of refraction. That's the intensity of the beam. So you see that this number here has a dimension. It's not dimensionless. Yes? They can probably in the next two slides. I will see this. We will measure basically the same frequency. Usually, what we measure here is basically the same frequency of the light that will shine the sample here. You can have other possibilities. For example, if you have a second order absorption, you can have a two-photon absorption, so you may have different frequencies of the light. You can shine, for example, a medium where you don't have this mirror symmetry, and you can induce a second-order light. So you shine, for example, with green light, you see blue light. But that's a process that we can also have here. But in this case, we will measure with the same frequency, the same color of the light. Pardon? Yeah. Yeah, because it's square here. Yeah. Well, okay. So in the former slide, you see that we make the description essentially with the scalars. But if you deal with some symmetry which is different from circle or a spherical symmetry, you can have some different susceptibilities depending on the orientation of the electric field and the orientation of the crystal which will receive this electric field here. So chi, as a matter of fact, is not a scalar, it's a tensor. And it depends essentially if you have the first order or second order or third order. So have this type of components, and you can have the sum, the different frequencies can be present here, as you see, okay? And what we will see in the following of this talk, we will measure this parameter here, essentially given the nonlinear index of refraction, nonlinear absorption. And we'll see some anisotropies that came there. So this is the complete way to write the electric field here. These are the permutations that you have if you are interested in the third order susceptibility. So this is the electric field, and the different polarizations which takes into account these different susceptibilities depending on how the electric field interacts with, for example, our cubic crystal, as I show you in a while. Well, so in the case of medium without this mirror symmetry, chi2 is the most important. It's named the second harmonic generation. So here it's possible to shine a sample with a particular color of the laser, and you will see a different color. A different type of frequency will be at the end of this experiment. So this will be very interesting, a very interesting experiment to measure the hyperpolarizability, which is a local property of the crystal in the case, and we can also make a relation between the hyperpolarizability and chi3, for example, which is a mean value or a mean property of this medium. Well, this I think I told you everything. So it's responsible for the change in the refractive index and the linear absorption. And this is a possibility to have what we named the two-photon absorption. And after you can have, when this electron here goes to this state E0, you have the emission of a photon with 2 omega. So you have a second order absorption here. So basically you have this state here. The energy of the photon, of one photon, is not enough to put the electron from this level to the first excited state here. So you are in the ground state. So the difference between them are basically twice the energy of a photon. You are interacting with your sample. So the absorption will have now a sum of the usual linear absorption and another one, which is named the nonlinear absorption of the sample, which is also a term proportional to the intensity of the beam. And this is the cross-section of the two-photon absorption, which is essentially depends on the number of absorbers that you have in your sample. So if you know this number here, you know the photon you are shining your sample. If you measure beta, you can have a very good measurements of the cross-section of the two-photon absorption. Well, so the nonlinear polarizability now is the one with chi3. If you have chi2 equal to 0 in this particular case, where you have spherical symmetry, the total polarization may be written like this, the first order and the third order, the susceptibility, the effective susceptibility of the material, and you can have mainly the intensity here, which is proportional to the square of the electric field, and the index of refraction is essentially different now, and this effect is named the Kerr effect, optical Kerr effect, where you have the modification of this index of refraction due to a very important interaction with the magnetic field. And the n minus n dot, which is essentially the difference between the index of refraction n minus n dot, is essentially this nonlinear part here, the intensity. So everything you know, except this term here. And this is the measurement we are able to do if you have a good technique to measure the nonlinear absorption and index of refraction. Well, take into account the different physical mechanisms that may take place in your sample when you interact with the electric field. Depending on this mechanism here, from the electric polarization to thermal effect and also Soré effect, this is the typical response time, which goes to femtoseconds until seconds. The Soré effect is essentially the following. If you have a colloidal sample, you have different particles homogeneously distributed in your medium. If you establish a difference of temperature between two surfaces of them, you have the migration of these particles from one part to the other of the colloid. Okay? This happens, can be thermophobic or thermophilic. It's thermophobic. The particles go to the cold part of the sample. Or thermophilic, they go to the hot part of the sample. This is mainly used, for example, you know, petrol here, oil. If you are in the surface of the sea, you have a temperature. If you go further, deep in the earth, you have a different temperature. If you have oil in between these two temperatures, this gradient of temperatures, you have different types of molecules or macromolecules that will go more in the surface or more in the deep of the sea. So this is important for a petrol company to see what they will do, if the will go down or not to down to take the particular molecule they are interested. So oil company invests a lot in the study, in the fundamental study of the Sorey effect. So as we are interested in the electronic polarization of our medium, we need to access times of femtoseconds. So we have to have a tool that will be able to prove our sample in this time scale, femtoseconds. So a pulse laser will be necessary to investigate the polarization of the ferrofluids. Well, so I think this I told you already. So to give you an idea of what is going on from the optical point of view, imagine that you have here a Gaussian beam. A Gaussian beam, this is the expression of this, this intensity as a function of the distance from the center of the beam, very intense in the center, less intense in the borders of the field. If we shine a sample here which does not present a nonlinear optical response, we have wave fronts here, we'll pass through the sample, and we have also, after the sample, wave front. You have not modification of the wave front if your medium does not respond non-linearly to the interaction with the field. On the other hand, you can have this type of behavior. Imagine that the velocity of light in the heat, the hotter part of the sample is different from this one. In the colder part of the sample, you have this deformation of the wave fronts, which looks like a convergent lens. No, this is named a self-focusing effect. So this happens for whatever all the sample you have, depending on the intensity of your beam. Your sample may behave like this, a self-focusing effect, or the other type of behavior is also possible. You have the difference in the velocity of light in the center, the hotter part, in the colder part here, and you have this type of divergent lens. So your sample will act like a convergent lens or a divergent lens. And what we will measure essentially is the intensity of the beam in the paraxial direction. I will show you in a while. So this happens when you have a nonlinear optical response of your medium interacting with a laser beam like that. Obviously, if this laser beam is not too high in intensity, this second order term will be very weak, and the nonlinear optical refraction and absorption will be essentially the linear one that we are used to. Well, what we will investigate? We will investigate basically something very simple, which is basically this magnetite nanoparticles, Fe3O4. Typical diameter, about 10 nanometers here. The temperature, they are in the super paramagnetic state, so the magnetic moment are not blocked. You are in super paramagnetic state. And we will investigate here 4 different colloids. The particle is always the same. So here we have the sample in a liquid carrier, which is an oil. Here is an oil, different types of oils, but oil, so non-polar liquid carrier, and a polar liquid carrier here. So all of them, in principle, if you are investigating the particle itself, should give us the same information, because you are looking basically to the same type of particle. And the other investigation we did to avoid, for example, thermal effects that could be present in a colloid, we have to work very hard to put out, to get rid of all the thermal effects present in an experiment, even in the femtoseconds time scale regime. We make the same experiment with thin films, essentially. These thin films, we take the colloids and we remove completely the solvent. It seems easy to be done, but it's not so easy, because to remove completely the solvent in this time scale for the sensitivity of the technique we are using is not a very easy job to be done. But with some effort of our students and postdoc, we are able to clean completely the samples from this paraffinic oil, synthetic oils, and water to compare with what we will measure basically in the colloidal samples. Well, so this is basically the structure of a magnetite. It has a spinal direct structure. When you have oxygens here in octaedral and tetraedral symmetry here, and the magnetic moment of them comes essentially from this part of the sample, because this one will be concealed by the other one, and these components of the octaedral side of the oxygen and the iron here will give the magnetic moment of the particle. So we will investigate essentially this type of structure now present in a magnetic particle, one magnetic moment only. Well, how experimentalists they have access to the measurement of chi3. This technique is a technique which was developed many years ago by this guy, and it's a very easy technique. I will show you in a while. And this name is Z technique because you will make a scan of your sample along the Z axis, because they name it the Z scan technique. You have a laser beam. I think I have it here. Okay. So imagine that you have a laser beam, a pulsed laser beam here. Okay. You have a lens. This lens will focus the beam at a particular position. This is the Z-axis, okay? And you have the detector here with an iris in the front, okay? So we will measure basically the rays, which are named the Paraxial Rays. So the rays which are essentially in this line, in this small hole in that position. So imagine if you have a sample which will diverge the field, the intensity measured here will be less, will be smaller than the intensity when the nonlinear optical effects are not present. On the other hand, if your sample has a focusing, self-focusing effect, you will measure an intensity here which is higher than the previous one without the nonlinear optical effect present. This is a beam splitter where you can take all the lights here and put in a detector. So all the light that will be transmitted by the sample will be taken here. So in the same experiment, you can have an idea of the refraction here. So you change the focusing of the beam and the nonlinear absorption also, because this detector here will give you good information about how your sample will absorb non-linearly, because the linear part is not taken into account here. Well, as I told you before, we are investigating electronic effects. So for electronic effects, we have to go to the femtoseconds time scale regime. So this pulse laser here, you cannot see the width of this, but the width is about 200 femtoseconds. So this is a 200 femtoseconds. This pulse speaker here, essentially what he does is diminish about 99% the intensity of this pulse here. And after 10 milliseconds, we put a shutter at that position, no light in the sample, and after we restart again. So we make this periodically. You may ask, for example, why do you put this shutter here and you don't work with this small pulses from 0 to about 2 seconds? The response to that is that if you take into account this small amplitude peaks here, if you sum in 2 seconds, what you will have is energy enough to increase the sample temperature and give you a thermal effect response, which is not an electronic response. So it's important to completely shut this laser here, and you have no laser shining in the sample. After another peak of 200 femtoseconds, this tree here, the amount of energy is very small. You will not change the temperature of your sample. So this is the important setup experiment, which will give us certainly a nonlinear electronic effect come from your sample. You don't have Soré effect contribution. neither the thermal optical effect contribution, which usually is present in this type of experiment. So, some numbers here, the wavelength of the laser, 800 nanometers. That's the intensity of this peak, maximum here. So is 16 gigawatts per centimeter square. So it's a high intensity beam necessary to give us the information about the electronic properties. W0 is mainly the radius here of the beam at the focus. So you don't have a point at that position, but you have something which is small and goes higher. And this is the dimension, about 20 microns, is the radius of the beam at the focus position. So what we do, we take the sample, we start the scan far from the focus. Obviously, the power of the beam is the same, but the intensity changes, because intensity is energy per time per square centimeter. So if we are far from the focus, you don't have a high intensity, nonlinear effects are not present. When you go near the focus, the intensity increases, so the nonlinear effect takes place there. And when you go far from the focus on that side, the nonlinear effects goes out, and you have again just the linear one. So this is the Z-scan technique, and we can do this for different time scales. If you are interested, for example, in thermal effects, you can form a thermal lens. And the thermal lens, the unique difference you have in this type of scheme is that you don't have a pulse speaker, you have a laser, a continuous laser, and you chop this laser. You put a chopper in the way of this beam. Chopper is basically a disc with some holes. You make this type of movement. When the hole is there, the beam passes. When it's not there, the beam is stopped. And with this, you can have pulse of about 20 milliseconds, 20, 30 milliseconds. You cannot do this type of experiments with a continuous laser beam because the time scale will be just milliseconds, and we need femtoseconds. So the important point here is the pulsed laser. Well, this is the real part of the susceptibility, the third order susceptibility. You see that it's essentially proportional to the index of refraction, the nonlinear part here. All the rest we know. It's something that we are able to measure independently. And the imaginary part is related to the absorption here. All the rest is known. So if you are able to measure this parameter here, you have access to N2 and beta. So this is the whole story. Well, to choose this 800 nanometers, you may ask, why did you choose 800 nanometers and not other one? The idea is that if you have the linear absorption here as a function of the wavelength of the laser, you see that here you have the minimum of the absorption as a function of the wavelength. So we choose this parameter here. And for example, if you have a second order absorption, two-photon absorption, you see you go from here to here, where the absorption is very high. Okay, so we choose basically this wavelength to do that. We have some technical questions here, how to make some corrections of this curve, but it's not necessary now. If you are interested, I can discuss after. So with these absorption curves, we can make this type of plots where you have basically here the absorption, age Planck constant, the frequency of the beam here as a function of the energy of the photon. So you can have an idea here about the band gaps of magnetite. And these are essentially one possible transition between the octahedral to tetrahedral sites and another one in proper tetrahedral. So here you have the absorption of one photon, and here you have the absorption of two photons, about that. So with this is our basic to choose the 800 nanometer to make the experiment. Well, so these are the typical results. First of all, we start with without the magnetic field, so the particles are essentially at random. Here is the normalized transmittance. The normalized transmittance is the transmittance you are measured in a particular Z position of the sample divided by the how I say that, the intensity, the intensity far from the focus. Okay, so far from the focus, you have essentially the linear behavior, here, and after that you have this type of behavior of the experimental points. So these are measured in the D1 detector, if you remember, the one in the paraxial direction. So we are measuring here basically the index of refraction. The red curve is a fit, so you will see what we have. And here is what we are measuring in detector D2, which is the complete intensity when you scan the sample around the focus. So far from the focus, you have the normalized transmittant equal to 1 here. And when you approach the focus, you have a decrease of the intensity due to the nonlinear optical absorption. This is also a fit. The terms, the expressions we are able to fix here is this one, closed aperture. The closed aperture is mainly the detector D1, so the refraction, and the open aperture where you take all the lights coming from the sample. So here is the index of refraction, and here you have the beta, which is the intensity which is changes. Here N2 and here beta. So you make this fit here as a function of Z. Z dot is a parameter, experimental parameter, geometrical parameter here. All the things we know, we don't know only N2 here and beta. So with this N2 and beta, we are able to measure here, to plot the absorption as a function of the number of absorbers that we have. You remember, we have something like that, no? That the beta is proportional to the number of absorbers. You have a very nice straight line here, passing by 0, 0. These are the colloids, and these are the thin films, okay? To see that we were able to remove completely the Sorey effect present, which could be present, and all the thermal effects that could be present also. So this is the measurement of this two-photon absorption on the cross-section in this complicated unity here, but the important point is that with this technique we are able to measure this parameter very well. Well, the point now is to see what is the effect of magnetic field. If you take a sample, like here, we put between two magnets here, permanent magnets, that will put a field here of about, we'll see the intensity of the field can be from 0, very far, one from the other. The maximum we can put in our setup is about 2.7, 2,700 Ørsted, and the sample at that position, and we are able to take the beam now and polarize the beam parallel to the magnetic field or perpendicular to the magnetic field. Okay, so we'll be able now to measure chi3 in the direction of the magnetic field and chi3 perpendicular to the magnetic field to see a possibility to have an isotropy here. So if I don't have too much time, I will pass by this. It's not so important, but this is without the magnetic field, okay? And when you put the field here, you see the black points here are with the field parallel to H. This is the intensity of H. And without field, open symbols there. So the nonlinear index of refraction basically does not change when you put this field. And remember that this field is between 0 and the first critical field. But in the case of the open aperture here, if you are perpendicular or parallel to the magnetic field, you have a modification of the absorption. And this will give us, please look at this, not so much time, but this one is basically the same. So this figure essentially tell us that N2 is basically independent of the magnetic field in whatever typical direction or relative direction you interacted with your sample. But the beta here is different. So here is the electric field perpendicular to the magnetic field. This is the behavior as a function of the field, okay? So here is field, here is beta. And open symbols is the E parallel to the magnetic field. So you see that you have an increase of this parameter here, beta, and a decrease, almost decrease, or almost constant within our error bars. But there is an anisotropy of beta, which is put in evidence in this experiment. To see what we had from the point of view of structure, we made a small angle X-ray scattering. This is a simple Sachs experiment. You have a X-ray beam, you put your sample in the front of it in a slab geometry, put the field or remove the field, and we see what you have without the field. Is something isotropic, is as expected, so all the particles are basically at random, no orientation. But here, when you put the magnetic field along the horizontal direction here, you have these two spots present indicating that you have the formation of needles. We have models to model what we are seeing there. Not going to these details, but this is the type of structure that the small angle X-ray scattering give us, present in the sample when you put the magnetic field. So this is typically what we got from the Sachs experiment. So you have the formation of this linear structure. Basically, the orientation of the magnetic moment in the case of a magnetite is along this 111 direction of the spinal structure. This is just to give you an idea of what I'm telling you. So it's along the main diagonal when that the magnetic moment is oriented. This is what you see in electron microscopy. 2 nanometers is this scale here. So basically, we are saying that we have this type of structure in the particles in the magnetic colloid. The magnetic moment is along this direction. So we are able to measure chi3, the component of chi3, along the main diagonal of this cube here, when you are in the electric field parallel to the magnetic field, and when we are perpendicular, as we don't have the possibility to freeze the sample, this movement is possible. We have a mean value in the direction perpendicular to 111. So essentially, it's this type of measurements that we have. So the components of chi3 along the direction of the main diagonal, this is the number we have there. And assuming when we measure something perpendicular to that direction, we have a mean value between two perpendicular orientation. This one is the x, I, and z. So we have this mean value, assuming that they are almost the same, not so different. This is the value what we measure basically, and give us an anisotropy of this constant, even in a cubic structure like the spinal structure. Well, so what we have as a take-home message, we were able to measure some nonlinear optical properties of these magnetic nanoparticles in the scale of about 20 nanometers, one magnetic domain only. When you have H equal to 0 without the magnetic field, this is nonlinear index of refraction. This is the nonlinear absorption. And when you have the different H different from 0, we were able to see an anisotropy, even in a cubic structure. Is the formation of these aggregates here, and this is the imaginary part of the susceptibility along the direction 111, parallel to the main diagonal of the cube, and in the direction perpendicular of this magnetic field, you have almost half of this number. And in the case of the presence of the field, this type of structure are present. So I think that is that. Thank you very much for your attention.